7.2 section is on logarithmic functions. Again, I'm going to be working from the Algebros notes packet, and I'm going to do audio voiceover. So, definition of a logarithm. Logarithm to the base b of x is equal to y. If and only if b to the y is equal to x. This notation, if and only if, is a pretty strong condition. It means not only if this, then that, but also the other way. If this, then that. So it's a stronger condition than just one way. All right, there does come with some caveats. B is greater than 0, it doesn't equal to 1, and the x is greater than 0. Okay, now recall that an exponential function is in the form of y is equal to some base to the power of x, okay? Whereas its inverse, the logarithmic function, is x is equal to b to the y. They are in fact inverse functions, which we will take advantage of. Now let's rewrite this in exponential form. And I'm going to follow what's going on up here. Okay, we want it in the form of b to the y is equal to x. Well, notice b is the base. In this case, the base is 5. Okay, and that b is taken to the power, and remember logarithms are nothing more or less than exponents. Okay, and so we write this as 5 to the third equals 125. And notice that is indeed a true statement. 5 to the third power is 125. Instead, let's rewrite this in logarithmic form. So now we're going to go from if this, then this. Okay. First of all, I'm going to take this cubed root and write it as a 1/3 power. And then notice the 1/8 is the base. So this is going to be log to the base of 1/8. All right. The 1/3 is the exponent. Okay. And so that's going to end up on the right side of the equal sign. And then the 1/2 is here. So we write this as this. Okay. So just keep in mind, you're basically kind of going back and forth from this form to this form. Keep this in mind when you do that. Some properties of logarithms that are important. If you have the logarithm of a product, then you take the sum of each individual logarithm, logarithm x plus the logarithm of y. This follows because when we take 10 to the x times 10 to the y, it's 10 to the x plus y. Remember, logarithms are exponents, and so the exponents would add. That's the product property. The quotient property is if you have the log of something over something else, it's the difference of their logs. Okay, so if they're in a numerator with each other, you add them. If one's in the denominator, you subtract them. And then another property that we're going to take advantage of fairly often is that if you have the log of a base to log of something to a power, we can pull that power out and write it as y log of x. Okay, we're going to use that quite a bit. So let's use these properties to, first of all, expand this. So notice this is a product, right? So I'm going to use the product property out there, the log of a product. This base log of to the base 4, that just kind of carries along. It doesn't play a role in what we're going to do. We just kind of carry it along. So the log of a product, we're going to take the log of the each individual ones and add them up. So for example, this is going to be the log of 3 plus the log of x to the 5th plus the log of y using the product property. One more thing we can do here is we can use the power property here to pull this 5 out and write it as a coefficient. Okay, so this is that expanded. Okay, let's do this one. Now this is complicated. I think the first thing I'm going to do is I'm going to pull that 5 in there. So this becomes p to the 5th, and then q to the 4th to the 5th becomes q to the 20th. Okay, and so now I'm going to take advantage of the quotient rule, where this is going to be log of p to the 5th minus the log of q to the 20th. Okay, quotient property. And then once again, I'm going to use the power property to pull these out front. And this is going to become 5 to the log of p minus 20 log of q. Okay. All right. Now let's condense this. Now this is a different example than the one in the packet. I think the one in the packet is overly complicated, so I'm going to do this one instead. We want to write this as a single logarithm. Okay. Now notice I have some coefficients out here. I'm going to, first of all, use the power property to put them back in, essentially. So I have log of x to the second, log of y to the third, and log of z to the 0.5. Okay. Now, notice that the log of x squared and the log of z to 0.5, we're adding those. Okay. Oh, okay. Then I'm going to change 0.5 to 1/2 just because. Don't necessarily have to do that, but they like it in that form, so we'll do that. Now I'm going to rearrange this a little bit. So I'm going to add the logs of x squared and z to the 1/2, and then subtract the log of y to the third. The product property means that the x squared and the z to the 1/2 are going to be together in the numerator, while the y to the third, by the quotient rule, is going to be in the denominator. And we're going to end up with this as our answer. Okay, so that's writing this first statement as a single logarithm. Okay. Okay, next example. This is example number 11, towards the bottom of the page. All right. And what we want to do is we want to get that unknown. We want to solve this for x. And notice the x is an exponent. Okay. Here's where logarithms become very useful, because we're going to get that x out of the exponent, we're going to use logarithms. Okay, using our power property. Okay. So I'm going to take the log of both sides. Okay, take the log of that side, take the log of that side. And then the log of 7 to the x power becomes x times the log of 7, using our power property. And this is where logs are extremely useful. They get the unknowns out of the exponent. Okay. Then it becomes a simple matter of dividing each side by the log of 7, and x is then the log of 41 over the log of 7. Which, if you operate your calculator, log of 41 divided by log of 7, turns out to be 1.91. Okay. All right. What about this one? Once again, we're going to take the log of both sides. Okay. Once again, we're going to take advantage of the power property. And then once again, we're going to divide by the log of 2. Okay. Pick up your calculators. Pause this for a moment. And what is the log of 0.25 divided by the log of 2? Should have turned out to be should have turned out to be -2. All right, some other reminders. Since the log of 10 is 1, because 10 is 10 to the first power, right? Then the log of b to that base is just 1. Okay, this is log to the base 10. If there's nothing written down there, that means it's log to the base 10, like our counting system. And so the log of b, if it's that same base, is just 1. All right. By extension, the log of b to the x is just x. Because anything to the 0 power is 1, then the log of 1, if it has an exponent of 1, that means it's 0. The power is 0. Okay. And then b to the power of log b to the x, these are inverse operations. They more or less cancel each other out, and you just get x. Okay, we're going to take advantage of that property as well in upcoming examples. Log to the base 10, we don't really write that 10 because that's called a common log. So we ignore that. If it's not there, it's implied, and that's log to the base 10. It's a common log. Log to the base e, that's special. That's called a natural log because that's based on nature. Okay, nature doesn't follow our counting to 10 system. It has its own system, and that's with e as its base. Okay, now let's do some examples. Okay, this is towards the top of the second page. The log of x is equal to this. Now, we want to undo this. We want to get this x out of the log thing, right? Well, the inverse operation for the log, just set like this up here, okay? We're going to take 10 to the log of x, okay? Because b to the log base of b of x is x. 10 to the log of x is x. So that's an inverse operation, okay? So by taking 10 to the on each side, it's going to more or less cancel itself out, and I'm just going to left with x. And according to my calculator, 10 to the 3.0876 was 1,223. I invite you to prove that to yourself. Next example, natural log of x is equal to this. So to undo this, the inverse operation over here was taking 10 to the, here it's going to be e to the. because e to the natural log of x, those are inverse operations. They cancel out, and it's just going to be x. Pause for a moment. Do this with your calculator. Find your e to the x button. It might very well be paired with the natural log button in your calculator. It might be a second function to that. E to the negative 0.9128. Pause. Determine that with your calculator. Should be 0.401. All right, one more thing that they'd like us to do, and that's finding the inverse of each function. Okay, now finding the inverse of this function, first of all, I'm going to write f of x as just y, so we have y equals 4 to the x. And recall how to find the inverse of a function. We switch the x's and the y's. Okay, we switch the x's and the y's. Now this x equals 4 to the y is the inverse of y equals 4 to the x. Now they want us to solve x equals 4 to the y for y. We want y equals. To do that, we are going to do what we did in previous examples. We're going to take the log of both sides. Then log of 4 to the y becomes y times log of 4 using the power property. And then divide each side by the log of 4. And we're done. Let's do this example. F of x equals 3 to the 2x. I'm going to write that as y equals 3 to the 2x. And then I'm going to take the inverse. X equals 3 to the 2y. All right. And then let's see. I'm going to take the log of both sides using the power property. I'm only going to pull the y out for now. Okay. The log of 3 squared is the same as the log of 9. All right. Okay, which we can then divide by, and so we get y equals log of x divided by the log of 9. Or, if you wish, you could have pulled the 2 out originally and then divided by the 2 and the log of 3, and you'll get 2 log of 3. Each of these answers are equivalent. All right, 2 more examples. Okay, let's do 19 first. So I'm going to replace the y f of x with the y. All right, and now I want to solve for y. Okay, now we want to isolate the log of x. We're going to end up taking 10 to the on each side, but I need to get rid of this minus 1 first. I need to isolate the log of x. We're going to do that by subtracting 1 first of all, sorry, my apologies. I forgot to we got to switch it first. Okay, so we get y is equal to log of x plus 1, and then we're going to switch them x equals log of y plus 1. This is the inverse, which we want to solve for y. Okay, and I want to isolate this first, so I'm going to subtract the 1. Okay, now we're going to take 10 to the x minus 1 is 10 to the log of y. But remember, 10 to the log of y, that's 10 to the log, that's an inverse function. So all we get then is y. All right, and so there's our answer right there. Finally, number 20, natural log of y is equal to twice natural log of x. The y is already there, it's not f of x, so we can just go ahead and switch it right now. So here's the inverse, which we now want to solve for y. Okay. Now you could isolate the natural log of y by dividing by 2, and you'll get a correct answer, although it'll be somewhat messy form. So instead, I'm going to take the 2 inside. Okay, and now I have the natural log of x and natural log of y squared, which we're going to e. Okay, and these are inverse operations. E to the natural log of x is just x. E to the natural log of y squared is just y squared. And then to solve for y, take the square root, and there's your answer. So those are the notes for section 7.2. Use these examples and additional ones in their video that I haven't done if necessary.